Okay, welcome to the fourth video in the playlist on chemical equilibrium. And what I want to do in this video is look at three different chemical reactions and their respective equilibrium constants. So I'm going to lay out three different chemical reactions. We're going to calculate, given equilibrium values for all the different components, we're going to calculate equilibrium constants. And what I want to do is bring that back to free energy, because I think it's really important for the student of equilibrium to realize what actually is controlling the equilibrium position of these chemical reactions. And the factor that is controlling the equilibrium constant is in fact free energy. And I've laid the groundwork for this in the first couple of videos that I did. And what I want to do now is show a closer connection to the value of free energy calculated for a chemical reaction and the equilibrium constant. Remember that it's the magnitude of the delta G and its sign that determines the extent to which a chemical reaction is going to shift to the right, producing products when you have combined quantities of the reactants in a reaction vessel. Now, what I want to do is take this a step further and show the connection between the delta G naught and the equilibrium constant. So we're going to rewrite this formula. So delta G naught is equal to minus RT ln and then the equilibrium constant K. So you can see the value that is given here when we combine, or we take the difference. Oh, and I see I've got a typo in here. When we take the difference between the enthalpy of a reaction and the absolute temperature times the entropy. So we're going to get a number here that's going to have a magnitude and a sign. And when the magnitude is large and the sign is negative, then after the reaction is over, the concentration of products is going to outweigh the concentration of the reactants. And when I say outweigh, I'm using that to mean outnumber. The fraction of products is going to be far greater than the fraction of reactants. And when the magnitude of delta G is large and positive, then the fraction of reactants left in the reaction mixture is going to be much greater than the fraction of the products. And when we're close to zero, that's a situation where the amount of products is equivalent, I'll write it this way, equivalent to the reactants based on the proportion. Okay, so based on the proportion determined by the coefficients in the balanced chemical equation. So let's take a look at these three chemical reactions. So the first we've seen before. Whoops. The first one we've seen before. And that's the reaction between iodine and chlorine to produce ICl. And the equilibrium concentrations that we have here, and when I say that, I mean and in this case it's going to be equilibrium partial pressures. So we set up our reaction, we let it come to equilibrium, and these are the partial pressures after equilibrium is reached. Now, to find the equilibrium constant, since we're in partial pressures for this reaction, all right, we're going to find a Kp, and the fixed temperature for this, in this case, in fact for all three examples, is 25 degrees C. So my equilibrium expression is going to look like this. It's going to be the partial pressure of ICl raised to the second power divided by the partial pressure of I2 times the partial pressure of Cl2. So we're going to have 1.638 atmospheres divided by 1.638 atmospheres squared divided by the partial pressure of iodine times the partial pressure of chlorine, which is going to be the equivalent of saying 0.181 quantity squared. So my Kp for this reaction is approximately 82. Approximately 82. Now my delta G for this reaction is a minus 10.9 kilojoules per mole. So I'm going to add, as we go, I'm going to add this information to the number line. So we've got a minus 10.9 kilojoules, and my K value is approximately 82. All right, now for the next reaction. Okay, so we're going to have the reaction of HC2F3O2. This is an acid. And it produces H3O plus the anion C2F3O2 minus. Again, this is at 25 degrees centigrade. Now, in this reaction, I'm going to do a very quick, because we dealt with my original example before in the first two videos. For this one, we've not seen it before, and I want you to understand that we're going to start out with a 1 molar concentration of this. And before any reaction, there's 0 of both products. But after the reaction occurs, the concentration of the acid HC2F3O2 is going to be 0.5821 molar at equilibrium. And the concentration of the H3O plus is going to be 0.41789, and the concentration of the anion C2F3O2 minus is going to be 0.41789, equivalent to the H3O plus, because both of these are 1-to-1 in terms of their stoichiometry. Now, we're calculating the Kc for this because we're in concentration units of molarity. And my Kc, I'm going to go ahead and just give you the calculation, is 0.3. Notice that this value is close to 1. Close to 1. All right, my delta G naught for this value, or for this chemical reaction, is 3 kilojoules per mole. It's a positive value, but it's comparably, by comparison to the equilibrium constant that we calculated for our first reaction. I'll call this reaction A, and this one reaction B. You can see that the delta G is considerably smaller. So it's a delta G that I consider to be within the realm of close to 0. So I'll write it in here. We're at we're at 3 kilojoules for this one. 3 kilojoules. And the K value is 0.3 for this. Okay, now the third example is another acid reaction, HC2H3O2. It's going to produce H3O plus this anion C2H3O2 minus. It's also at 25 degrees centigrade. And like the other reaction, we're starting with a 1 molar concentration of it. All right, and at equilibrium, we're going to have 0.9957 0.76 molar of the acid, and we're going to have 0.00424 molar of both H3O plus and the anion together. When you calculate the Kc for this, and again we're calculating a Kc because we're in concentration units of 1 molar. And just to be clear about this, the numerator is going to be 0.00424 quantity squared, because we've got 0.00424 times 0.00424. And then this will be divided by 0.99576. Okay, now this Kc is about 1.8 times 10 to the minus fifth. This is what I consider a small equilibrium constant. All right, so let's write in, and the delta G naught for this reaction is equal to 27 kilojoules per mole. So this is a comparably large number in magnitude to this number here, except that it's opposite in sign, right? It's a positive value. So I'm going to write its value over here. It's about 27 kilojoules per mole. So you see, example C is way down here on our scale to the right of where sample B was, or example B. And the K for this is equal to 1.8 times 10 to the minus fifth. Okay? Now, let's bring all of this together. So you can see that when delta G is negative and relatively large, that you're going to get a K value. You're going to get a K value, which is much greater than 1. And for these values, where your delta G, and I want to emphasize this, either positive or negative, the issue is being close to 0. Being close to 0. All right? And in this case, the K value, I'm going to change the color of this. The K value is going to be approximately 1. Approximately 1. And then when we end up with a chemical reaction whose delta G is positive and relatively large in magnitude, then you can see that the K value for this is going to be much less than 1. Okay? Large positive delta G, K very much less than 1. K very much less than 1. When delta G naught plus or minus is close to 0, like it was with example B here, where Kc was about 0.3, then the K value is going to be close to 1. Close to 1. All right? And when delta G is large and negative, then the K value is going to be greater than 1, and the fraction of products to reactants is going to be a large number, K greater than 1. So you're going to find way more products in the reaction mixture of a reaction being controlled by delta G where it's negative versus the amount of products that you find in a chemical reaction where delta G is large and positive. For delta G's that are close to 0, your reaction mixture is going to be a mess once the reaction reaches equilibrium, because there are going to be comparable amounts of products and reactants based on the stoichiometry of the reaction. And with this, I'm going to close the video.